So hi, I'm Ziqi from Zhejiang University. It's a pleasure to present our work on property existence inference against generative models. This work was jointly done with my students, but they were not able to attend the conference, so I present our paper. So our work focuses on the image generative models like diffusion models, GANs, and VAEs. So recently, these image generative models are used to generate very highly realistic images from a certain text prompt as input or even without any input. And however, these image generative models, they suffer from many privacy problems. For example, the attackers can infer sensitive information about the unpublic datasets from the query results of the target models. So among all these attacks, the popular inference attacks include the membership inference and the property inference. So the membership inference aims to infer whether a specific sample is in the training dataset of the target model. So assume there are these two persons in the dataset. Membership inference regards the people like with the gray and green rectangles as member, but with blue as non-member. So this is membership inference. So different from this existence judgment, property inference regards a training dataset as a type of statistical data, and it aims to infer the accounting ratio of a specific property in the training dataset. For example, in this case, the attacker can infer the female ratio in the training dataset. So literally, in our work, we combine these two types of privacy inference and propose a new inference named property existence inference. So it aims to infer whether a specific property is in the training dataset of the target model. So for example, let's assume this dataset consists of images of many persons, and our attack is going to infer whether a certain person is used in the dataset instead of inferring whether a specific given image of the person is in the dataset. So compared with the membership inference, so the attackers in our settings don't need to have exactly the same sample as in the training dataset, which we believe makes our attack more practical. And previous studies of the property inference usually focuses on properties that account for a large proportion, for example, more than 10% of the training dataset. So however, we argue that inferring the existence of such a large proportion may not actually leak sensitive information. For example, it does not make sense to infer whether there are females in this world. So sometimes we think that it is the data accounting for a very small proportion that attracts the attackers. So our property existence inference attack considers such data with a small proportion, for example, less than 0.1% of the dataset. So for certain attackers, we consider these three questions. The first one is, does Stable Diffusion use Van Gogh's artwork as training data? So this is property existence inference. And does Stable Diffusion use the Mona Lisa's smile as the training data? So this is membership inference. And how much females' photos does Stable Diffusion use as training data? So this is property inference. So in our story, we assume the black box scenario where the attackers can only get the generated results of the target model. So we design our inference method with the intuition that the generated images can carry the property that the generated models have seen in the training dataset. And we are going to utilize this similarity to achieve the attack goal. So our approach can be divided into 3 stages. In the first stage, we are going to train a property extractor to learn the feature of the target property. And in the second stage, we propose a novel similarity score to effectively measure the similarity between the target property and the generated images. And finally, we choose a threshold to distinguish the in property from out properties. with the computed similarity scores. And so in the first stage, we designed the property extractor as a network, neural network, trained with a triplet loss function. So specifically, we use a triplet data set containing 3 images for each data point. For example, a base image, a positive image, and a negative image. So the base image is of the target property, for example, a person in this figure, and the positive image is with the same property with the base image, and the negative image is with a different property. So we can train a CMS network to embed these images into the embedding space, and we train the network to minimize the cosine distance between the base and the positive embedding while maximizing the cosine distance between the base and the negative embedding. So finally, in this way, we can train the network to classify images with the same target property. And with this property extractor, we can extract the embeddings of the anchor images, which the attacker, we assume the attacker can have. The anchor images is with target property, and we extract the embeddings of these anchor images and the target and the generated images of the diffusion models or the generative models, and we compute their similarity score by the cosine similarity. And then we sum up the top K similarity score at the naive similarity score. So why we call it naive is because in our experiments, we found that the naive similarity score does not perform well. So this is mainly because of the embedding uncertainty of both the anchor images and the generated images. So in order to remove these uncertainties, we propose 2 techniques named the similarity score smoothing and likelihood calibration. So we use a softmax method to smooth the value of the original scores in the similarity score smoothing. And if the adversary does not have a well-crafted input to control the generation process, so the images will be randomly generated from a predefined latent space. So in this case, the generated images will also exhibit uncertainty. So in order to mitigate this uncertainty, we use likelihood calibration. So specifically, we introduce a likelihood test to calibrate the similarity score by approximating the similarity distribution. So we focus on the reference out distribution, which is a distribution of similarity scores between the generated images and the reference out distribution dataset. So the reference out distribution indicates a general level of similarity for data with the out properties and helps to mitigate the bias of the similarity introduced by the generated images. So for each anchor image, we calculate the corresponding probabilities under the reference out distributions of all generated images and add them up when calculating the similarity score as the final score. So with these 2 techniques, our experiments have shown this effectiveness in distinguishing the improperties from out properties. So for example, as in the right histograms, we can see that the 2 distributions of improperty and out properties are further separated in the second row compared with the first row. So the last stage is going to determine a threshold to distinguish the improperty and out property. So to determine the threshold, we first train shadow models with a training set sampled with the training set are sampled from a randomly sampled distribution. And next, we select the properties used for training and those not used for training to obtain their corresponding similarity scores. And we model the scores of these 2 types of properties as Gaussian distributions, and with means mu0, mu1, and standard deviation, sigma 0 and sigma 1. And the adversary can choose the threshold based on different false positive rate requirements. So in our paper, we adopt a previous work and we set the threshold as in this equation. So in our experiments, we adopt the following target generative models, including diffusion models, GANs, and VAEs. And we evaluate our approach on 3 datasets, ImageNet, ComCars, and SlabHQ. So in our experiments, we use the metrics of AUC, accuracy, and TPR at 1% FPR, which is a widely used metrics for inference attacks. And we find that most of the generative models are vulnerable to the property existence inference. For example, on the ImageNet and the ComCars dataset, the AUC of our attack is larger than 90%. And in order to investigate the effectiveness of our attack in generative models for real-world scenarios, we also perform our attack on the open source model, Stable Diffusion, and trained on the Lijin dataset. We use the artistic style of works as the inference goal, and to assess whether any given artist's works are used in Lijin. Because the out properties like clear information about the artist used in the prompts to carry the Stable Diffusion, so we adopt the imprinting method to obtain the generative samples. So specifically, we randomly crop 3/4 of the image and expect that Stable Diffusion will have a better reconstruction performance on the images with improperties. And we calculate the sum of the cosine similarities of the embedding vectors of the before cropped images and with the target property, and the after imprinted images as the score of this property. And the results of the evaluation demonstrate that our attack is effective for models trained on Stable Diffusion, this kind of large-scale training on the Lijin, the large-scale training sets in a real-world scenario. The AUC is around 0.75. To evaluate the effect of the size of the training dataset, we change the size of the training dataset for all 3 types of generative models, and we find that there is no large difference in the inference results. So we believe that the primary reason for our attack, it may not be overfitting, and the increasing the size of the training dataset is not an effective way to defend our attack. And besides, we also evaluate the effect of adversarial knowledge on the results with an increasing size of generated images carried by the attacker and an increasing number of anchor images. So the adversary will get a better performance of the attack, which is obvious. And we further explore the effect of the property granularity. And with a finer property granularity of birds and dogs, the inference performance dropped. So selecting properties at a finer granularity level will result in a higher inference difficulty. So in conclusion, in our paper, we propose a new inference attack called property existence inference against generative models, and via comprehensive evaluations, we demonstrated its effectiveness. Okay, thank you. That's our presentation.